will record every 5 minutes.
Okay.
I try to reduce the 3 minutes because we don't have enough time.
There's no screen on the data logger, so we can't see what the temperatures are at the moment. We have to wait till we go back and plug it in.
Yeah, I have to go back to my office.
Okay.
Because I have some software to analyze.
Okay.
Yeah.
This kind of data could ultimately help predict future eruptions. With little time remaining, Benoit is also determined to squeeze in one last experiment that could reveal pressure building within the volcano.
I would like you to follow the drone with binoculars to be sure I don't crash it.
Years of observations around the world have shown that before an eruption, increasing pressure can change the shape of a volcano, making it swell. Perhaps the most extreme example is Mount St. Helens in Washington State. In 1980, the north side of the volcano bulged outwards some 270 feet. Just a month before its violent eruption. Usually, scientists are looking for much more subtle changes, which can take months of monitoring with a whole range of ground-based sensors. That's not possible here. So Benoit has come up with a high-tech solution.
I'm using a drone to take pictures of the big crater in different viewpoints, and with this set of images I will be able to create a 3D model of the pit crater.
The computer model Benoit creates is a 3D snapshot of what the crater looks like today. Comparing it to images captured on future visits will allow him to spot small changes in the terrain, which may precede an impending eruption. Benoit has just enough time to finish his survey. The 2 hours are up, and weather is closing in.
We are a long way from the helicopter, and there's a huge bank of cloud that's coming our way, so I think they take the weather window and we bug out.
If the storm hits, the helicopter will not be able to take off, leaving the team stranded on the summit.
If you need me to carry anything, let me know.
Okay.
Some space in my pack.
And we still need to pick Kayla up on the way as well.
Yeah, okay.
She's still over there doing a gas box.
It's been a frustrating day for Kayla, who hasn't managed to capture any useful data.
It's just so hard to work in places like this where access is nearly impossible. And then when you get access, you have 2 hours. It's just not enough.
Even so, this rare visit has been worthwhile. They've confirmed that the lava lake that appeared in 2014 is no longer active, raising the possibility that the volcano may once again be building towards a major eruption. If so, the new monitoring equipment they left behind may help forecast that event. As the team departs, they turn their attention to another goal of their expedition, investigating what makes this part of Africa so intensely volcanic.
It's amazing from up here the view you get. From the ground it was spectacular, but from here it is absolutely something else. This flat land with these volcanoes just punching through absolutely everywhere.
The entire area is filled with evidence of volcanic activity. Each one of these small hills is an extinct volcanic cone. But what is the impact of living in such a volcanic landscape? To find out, the team travels to Goma, a city of almost 1 million people that lies south of Nyamuragira and another giant volcano. Nyiragongo. Nyiragongo last erupted in 2002, sending rivers of lava into the heart of Goma, causing death and destruction. The city has since recovered and is growing. Today, Chris and Aldo are heading to a local boxing gym.
Wow, check this out.
They're here to learn about the relationship between the area's volcanic history, its ongoing instability, and what local people are doing to address the trauma of violence. Continuing unrest here means that children often have little choice but to fight in the armed gangs and militias that operate around Goma. Some of the men in this gym were once child soldiers. The discipline of boxing provides a way for them to escape their violent past. The continuing unrest and use of child soldiers are driven by the extraordinary mineral wealth of the region, especially one mineral that plays a crucial role in modern life.
This is the mineral coltan, this dark coloured mineral here. It's the kind of mineral I'd expect to find in an area like this. And any touchscreen phone, laptop, anything with a transistor on will have tantalum, which is the tan of the coltan.
The explosion in smartphones and other electronics means coltan is in constant demand. Even small mines can generate huge profits. But in this region, militias control many of the mines. The income means they can recruit young people, fueling the ongoing violence.
It's very hard to hold this in your hands, knowing how much we desire it and knowing what it leaves behind it and where it comes from.
The head of the gym, Kibo Mango, is a former child soldier who now tries to help young people rebuild their lives.
Are you happy for us to join in some training?
Aldo's fascinated by Kibo Mango's story because, like him, Aldo became a soldier at an early age.
So Kibo, when did you join the army?
Nilikuwa na miaka 14 nikaingia muarme.
Which is 2 years younger than I was when I joined up. How long did you serve in the army?
Miaka 21.
Although Aldo joined the Royal Marines at 16, legally he couldn't see frontline action until he was 18, unlike Kibo Mango and the young people here.
I wouldn't mind noting that what Kibo Mango's doing here to run this boxing club is partly for his own therapy. As a child soldier, he's going to see some pretty nasty stuff.
After the workout, Aldo has a chance to take on the man himself. Kibo Mango is a former Congolese champion.
Kusaidia juu ya sira makomba ishi kama unakuwa na sira mwingi na kwa pia paraporo ya kufanya mjia ya kufanya mkono na wamingi mapaji na risikape wakosa bazazi waliotupiwa barabara nikaishe unaona pale shi tuko na mali mingi sana hapa barakia wana mafuta mjua shatu na mwae unakutaka kukusiwa na mwae wanakaanza tena mtoto wanamrudisha huko.
In a poor and job-starved area, militias are one of the few sources of money and employment. It's a vicious cycle. The chaos in the region helps gangs control the mineral wealth, and in turn, The mineral wealth allows the gangs to maintain the chaos. There are efforts underway to break the cycle by promoting a more sustainable use of the resources created by the volcanoes. They focus on the Virunga National Park, a vast nature reserve covering around 3,000 square miles. Its fertile volcanic soils make it one of the most diverse parks on the planet, and one of the few places where it's still possible to see mountain gorillas. These highly social animals thrive in this lush forest habitat, eating mainly leaves, shoots, and stems. Thousands of people come to see the gorillas, generating cash that's used to create local jobs. But following attacks by poachers and criminal gangs, the park had to close temporarily. Another setback for a region where volcanic ridges have the potential to create a very different future. But what makes this area so volcanically active in the first place? It's a question the scientists are determined to answer.
From the helicopter, I got like almost a once-in-a-lifetime view of the entire volcanic landscape. And what really struck me was the amount of volcanism, the amount of volcanoes here. We have hundreds and hundreds of them.
This extraordinary concentration of volcanic activity is related to a vast chain of mountains and valleys. The East African Rift. It's a massive geological feature, stretching nearly 4,000 miles up the eastern side of the continent. And the Goma volcanoes are at the midpoint of the rift. The Earth's outer crust is divided into giant slabs called tectonic plates. Along the East African Rift, the tectonic plate is splitting, and the two sides of the rift are moving away from each other as the continent slowly rips apart. If the split continues over millions of years, a new ocean and continent will form. But many rifts don't fully develop. The waters of the Mississippi now fill the scar left by a failed rift when a huge section of what's now the Midwest started to tear apart around 1 billion years ago and then stopped. Will the East African Rift also fail? The answer hinges on a controversial theory.
So one thing it could be is something called a mantle plume. That's a column of deep, hot material which is rising up towards the Earth's surface. As it comes to the Earth's surface, it can weaken the plate and it can actually force the plates apart. But some of that melt, some of that magma can also come out onto the Earth's surface and build volcanoes.
The Earth's mantle lies between its dense core and its thin crust. The presence of a mantle plume, a huge column of heat and melted rock rising from deep beneath the region, would explain why there are so many volcanoes here. If a plume exists, then the enormous heat and energy it brings could keep the rift active long enough to split Africa apart.
Like all geological theories, we really need to go out into the landscape and look for additional evidence.
So along with Kayla, Chris goes on the hunt for evidence of a distinctively deep upwelling of heat and magma, the signature of a mantle plume. The first place they want to look is one of the extinct volcanic cones common in the region.
I'm really interested to see some of the smaller cones because we've been looking at Nyiragongo, Naimurugura, the big boys. There's so much information that the smaller cones can have too.
Their destination is Lac Vert, the Green Lake, just outside Goma.
Wow, look at that.
Today, it's a 300-foot climb down from the crater rim to the lake. People bathe and wash clothes here, but around 500 years ago, this was an active volcano. Chris and Kayla want to know what sort of eruption formed Lac Vert, and whether it could be linked to the presence of a mantle plume. They also want to find out if this volcano could erupt again, and what that would mean for the city of Goma. They start by examining the rocks that make up the volcanic cone. For many years, the sides have been quarried, so with a little effort,
You gotta go over the head.
Over the head?
Yeah.
it's easy to get their hands on some samples.
None of this is actually lava. This is all ash. These are all ash deposits. And that means this was magma that came up through the ground, was exploded under the surface, and absolutely ripped apart into very, very fine pieces that you can see here. Imagine how much energy it would take to take solid rock and just explode it into these tiny, tiny bits. That screams to me that there was an interaction with the water when this actually erupted.
Goma sits in the middle of a string of craters like Lac Vert, each formed by explosive eruptions, and each capable of delivering a devastating blast. The eruptions are caused by magma welling up from underground. When the magma hits a layer saturated with water, the extreme heat instantly turns the water to steam, triggering a powerful explosion. This generates huge amounts of fine-grained ash, just like the deposits found here. Clear evidence that Lac Vert was formed by this type of explosive eruption. The sides of the crater also reveal something else. This wasn't a single event.
What strikes me as somebody who's interested in sedimentology is how many layers of rock there are like this. The layering in the rock behind us, I wouldn't want to go over there and count them, but there's clearly hundreds and hundreds of giant explosions associated with this catastrophic eruption.
It may be about 5 centuries since the last eruption, but the danger of a new one is very real.
We've still got lots of volcanism here. We're still right next to the lake. We can see in Lac Vert the water table is right here. There's all the ingredients there for this to happen again.
A powerful new eruption along this densely populated shoreline, or in the city of Goma itself, would have a devastating impact. But there might be warning signs. As magma moves up towards the surface through underground cracks, it forces the earth apart, creating swarms of mini earthquakes that instruments called seismometers can detect. Joshua Subira of the Goma Observatory explains that seismometers have been placed next to the volcanoes and along Lake Kivu, near the city of Goma.
Ici, on a un outil de surveillance qui donne en temps réel ce qui se passe sur les deux volcans et dans le bassin du lac Kivu. Il y a possibilité de localiser ces événements sismiques et de comprendre par où il peut y avoir une éventuelle éruption.
This network of seismometers is an essential tool in the effort to forecast eruptions here, where so many lives are at risk. But neither seismometers nor cones like Lac Vert can tell Chris and Kayla whether the heat and magma that create these volcanoes is coming from a mantle plume
think we need to get deeper into this landscape and try and uncover what's really driving everything from the biggest scale sense.
One place they have yet to explore could hold the answer. Lake Kivu. Joining Dario Tedesco and Mathieu Yalire from the Goma Volcano Observatory, Chris and Kayla head out on the waters of the vast lake that lies directly south of Goma. Lurking in its depths is a huge hidden danger, worse than anything they've seen so far. It could also hold a vital clue about whether a mantle plume is driving the volcanic activity here.
So maybe now we're ready to put this thing in the water.
The
Yeah?
key is to get a water sample from the deepest part of the lake.
Let's try not to lose everything.
Mattia and Dario drop an open sample bottle down to a depth of 55 meters, about 180 feet.
50 meters. And here we are 55. Yes. If you want to see it,
I'll stand up.
goes.
Yeah.
We leave it.
A heavy weight is then sent down the rope to trigger the mechanism that closes the bottle.
You can feel the weight of that. You feel as I'm dragging it up, pushing the water out of the way as I bring this thing up.
I think so. Yes, here is it. And look, look at the gas coming out. Can
Oh my god.
Wow.
Like a carbonated drink, the bubbles consist of gas suddenly released from the water sample. This is the danger lurking in the lake.
When you open.
You can hear it.
It's like opening a bottle of pop.
Yeah, exactly. You
Looks
see,
like
you see
a
this
soda. It's all completely carbonated.
is 99% is carbonate.
99%.
Yeah.
The bottom of the lake contains the potentially lethal suffocating gas, carbon dioxide. It's given off by the constant volcanic activity beneath the Goma region, seeping into the lake from the underlying bedrock. Its presence is a serious threat. Lake Nyos in Cameroon also has volcanic carbon dioxide trapped in its depths. On the night of August 21st, 1986, a giant lethal pulse of the gas escaped from the depths of Lake Nyos, flowing over the shoreline and into surrounding fields and villages. Almost 2,000 people suffocated as they slept. And Lake Kivu is far bigger than Lake Nyos.
All the lake has a huge amount of CO2, about 256 cubic kilometers.
That's enough gas to cover an area more than 50 times the size of New York City and a suffocating layer 20 feet deep. The risk is that a volcanic eruption or earthquake could destabilize Lake Kivu, releasing its carbon dioxide gas, threatening the lives of thousands of people. But there are efforts underway to prevent that. The group is going to see an experimental project.
This is one of the most amazing things I have ever seen. We're in this glass flat bay, and all of a sudden you come to this platform, and it's just all hell's broken loose.
It's a massive amount of pressure. It's almost like a geyser. Just
It is a geyser.
It is
a geyser. And you don't see the geyser itself just because there is something on top, a core that is just 50 meters in order not to let the geyser flow.
Salty water, another product of volcanic activity, seeps into the deeper sections of the lake, forming a dense layer that acts like a lid, trapping the carbon dioxide below. The aim is to find a way of slowly releasing the trapped gas at concentrations that don't endanger people. A pipe runs down from the platform into the carbon dioxide-rich layers. The water saturated with gas flows up the pipe in a controlled release, allowing the carbon dioxide to mix with the air, making it harmless.
This is a pilot to see if there is a way to degas this part of the lake. If it succeeds, we will make a very big one to put a very big amount of CO2 in the air.
The controlled release of the carbon dioxide reservoir at the bottom of the lake could prevent a future disaster. But it's a massive project and very expensive. Although efforts to commercialize methane or natural gas, also found at the bottom of the lake, could help defray the cost. Meanwhile, the dangerous carbon dioxide in Lake Kivu provides a valuable clue to what's driving the area's many volcanoes.
Where is the carbon dioxide actually coming from?
Most of the carbon dioxide that we collect all over the lake comes straight from the mountain. This is probably the best findings we have.
The carbon dioxide they collect here bears a distinctive chemical signature, revealing its origins were deep in the mantle, the thick layer between the Earth's crust and its core. Here in the Goma region, the Earth's mantle is at least 20 miles beneath the surface. Only a giant mantle plume, a huge upwelling of magma, could bring gas up from such a depth.
The idea that there's a mantle plume underneath here, there's some evidence at the bottom of the lake, I just never thought that would be something we'd find out.
It's really the last piece of the puzzle in this landscape, I think.
The existence of a mantle plume, bringing up extreme heat from the depths, means the East African Rift will likely continue. Africa may eventually tear apart. Fortunately, not for many millions of years. But the scientists believe the energy unleashed by the plume explains the extraordinary volcanic activity witnessed during their expedition.
The CO2 is sitting in the bottom of this lake, all of the gases, the sulfur that we can smell, it's all coming straight out of the mantle. It's just streaming off this upwelling plume of material that's delivering heat, energy, chemistry to the whole landscape, to the volcanoes we've been on, the bottom of this lake. It's all connected to the same huge process.
After 3 weeks, the expedition has come to an end. It's been grueling, but the team has gained unprecedented insights into the volcanoes that dominate this region. On Nyamuragira, their aerial survey is an important step toward predicting future eruptions. And in the depths of Lake Kivu, they found evidence that a vast mantle plume drives the region's intense volcanism, which may ultimately split Africa in two. The people here live side by side with the geological forces that are reshaping the face of our planet.
If you live in this amazing, amazing place, you can live with the hazards, but those hazards cannot be at the front of your mind all the time. It would just stop you from doing anything, I guess.
The knowledge gained on the expedition, working with local scientists, is vital to better prepare the people of Goma for future eruptions, which are bound to occur.
We have active volcano now. The city became very big, many people in Goma. The gas in Lake Kivu, it will make a problem. Maybe we have to monitor and continue to monitor, make a warning in time.
These forces can be understood, but never completely controlled. This will always be one of the world's most extraordinary places to live. A landscape of both deadly hazards and incredible wonders.
We have this absolutely vast volcanic landscape here, and the people living right on top of it. It's my hope that people can learn to understand that landscape better in order to not only protect themselves, but also to reap the benefits from it.
From pain pills to fentanyl,
My parents' worst nightmare. To find my kid not breathing.
a deadly epidemic.
Overdose is the #1 cause of death for people under 50.
But there are solutions.
We have life-saving medications.
A brain disorder that can be treated.
Let's embrace addiction as a disease, bring it within the house of medicine.
Addiction. Next time on Nova.
This Nova program is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS. Nova is also available on Amazon Prime Video.
It is pushing the cylinder up with a force equal to the weight of that water displaced. And how much water is displaced? The volume of the cylinder. And how much is the volume of the cylinder? The volume of the cup. Accordingly, with the equilibrium destroyed because there is a lift or buoyant force here, I am now going to pour some water into this little bucket. Water, 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 pour, pour. When this bucket gets full, what will we see? An absolutely enchanting thing. We will see the equilibrium restored. Now I have such a bucket and cylinder. There's the cylinder, there's the bucket, and I have put it in equilibrium on the scale. Now I'm going to bring up this water and submerge the lower solid cylinder. I hope you see that the equilibrium has been destroyed. The balance is no longer in balance. Oh, I came up too high. Now I am going to fill the little bucket. I'm having a little trouble here being steady. I'm going to fill the little bucket, and the equilibrium, which does not now exist in the scale reading, will be restored. Watch me now. Oh, I filled it over much, and there's a very high meniscus. So, Archimedes bucket and cylinder. The proof is very beautiful. A body is buoyed up by a force equal to the weight of the water displaced. Now, regarding buoyant forces, bodies that sink and bodies that float. Here is a vessel of water, and here's a piece of wood. Floats. Here is another piece of wood. Wood, water. Heavier than water. Lignum vitae. Here is a piece of wood. Heavier than water. So there are woods that sink and woods that float. Their densities being less or more than that of water. Now regarding bodies submerged in liquids, I have here something absolutely enchanting. Here is a vessel of water in which I'm going to put a wooden ball. There. It sinks about, 5/8 or something like that. Now here is a vessel of mercury. Vessel of mercury. I'm going to put the ball in the vessel of mercury. Watch it. It doesn't sink at all, hardly. Hardly. It rides on the very surface. But that's wood. Very light. How about steel? Oh, you know that the specific gravity of steel is about 7 or 8. The specific gravity of water is 1. You know that steel sinks in water. Watch it. Sinks to the water. By the way, I say steel sinks in water. On an earlier program on surface tension, the strange behavior of the free surfaces of liquids, I showed in a demonstration where I float a steel needle on water. So steel can be made to float on water. But how about the steel ball in the mercury? Watch it. Oh, this is something. There it is. There it is. The steel floating on the mercury. This is a marvelous thing. Let me use a larger steel sphere, because this is enchanting to see. There it is. Steel floating in mercury. Now, talking about Archimedes leads me to show you a classic mosaic. You remember that Archimedes defended the city of Syracuse when it was attacked by the Romans under the general Marcellus? And then Archimedes was put to death by a Roman soldier who ran upon him while he was doing a demonstration in the sand. So here is that mosaic, which I hope you will see. There is the Roman soldier urging Archimedes, come to my general Marcellus. And Archimedes begged him, let me finish first my demonstration. And here is another monument to Archimedes, which shows him holding a mirror. This is a little glossy and hard to see. Holding a mirror with which, you remember, he set fire to the enemy ships far from shore. So, what have we discovered here? The remarkable principle of Archimedes that a body submerged in a liquid is buoyed up by a force equal to the weight of the liquid displaced. Now, Archimedes, as you know, apart from being a natural philosopher of the first magnitude, was also a mathematician. And I want to tell you quickly about some things he discovered of a mathematical nature, because they are enchanting. And here they are. Here I have a right circular cylinder. And here I have a right circular cone. And here I have a sphere. They are the same altitude and the same radius. And what did Archimedes discover? He discovered, by playing with these, filling them now in turn with sand, that the volumes were uniquely related in the ratio of 1 to 2 to 3. I'll leave it to you to discover how that ratio goes with respect to the bodies. Now, in his later years, having made many discoveries of great moment and significance, he was asked what he viewed as his greatest, and he referred to this, the ratio of the volumes of the cylinder to the cone to the sphere, and asked that when he dies, such a matter be put atop his tomb, which shows a cylinder, a sphere circumscribed by a cylinder. So here is a sphere about which is circumscribed was put on top of Archimedes' tomb, buried near Syracuse. Where are we then in this dialogue? Archimedes, 3rd century BC, who must certainly rank with Newton of the 17th century and Einstein of the 20th. So, next time you go to the sea to bathe, remember Archimedes. And when indeed you take a bath in your bathtub and you submerge yourself in the water and the water rises, remember the affairs here, which revealed that beautiful fact which we use abundantly. Because after all, this is why ships can sail on the sea and submarines under the sea and airplanes above the sea. And I thank you for your attention.
$782? That's a great deal. Liberty Mutual? That's a great company.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, again, still. And my principal business is physics. And today, a program which I entitle Some Extraordinary Adventures. Some Extraordinary Adventures. Consider the following, and some of the results you will hardly believe. I have here a flask with some water in it, and I have applied some heat from below, and the water is boiling. We say the water is boiling when the vapor pressure given off by the water, delivered by the water, is equal to the atmospheric pressure on it. Now I am going to remove that boiling flask to a cold tripod, and I'm going to shut off my gas burner, shut off the gas, and I have put this tightly stoppered on this cold tripod, and you see an astonishing thing. Well, somebody says, what's astonishing? The water stopped boiling pretty nearly. Yeah, the water stopped boiling pretty nearly. It'll stop altogether pretty soon. And I have it tightly stopped. Now what am I going to do? From time to time, I'm going to lay my hands, which are colder, of course, at a lower temperature than that flask. I'm going to lay my hands on there, and the water will boil. Now, because it's too hot for my hands, I'm wetting my hands a little bit in some ice water. Now, watch, 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 watch. Oh, yes. Notice the laying on of hands. I have boiled the water. Now, you must give me your undivided attention to another matter. You see, I am boiling water there by applying heat. But over here I have another demonstration where I'm going to boil water not by applying heat, but by taking heat energy away, and I'm going to boil the water so fast that it's going to get so cold by evaporation that it freezes. Now, who'd believe that? So here's what I have.